Because the number of times I've talked to infrastructure engineers, be you a network, a storage, compute, doesn't matter, where there's just a misunderstanding, a confusion about why developers have felt this need to run off to public cloud services. Why is it this x86 virtualized data center that we've perfected over the years is no longer good enough? And a lot of times we don't understand because we're not in their shoes. We don't understand the challenges they have, the decisions that they're making, why they're headed in that direction. And that's the goal of today's session, is to help us as infrastructure people kind of put ourselves in their shoes a bit, understand their challenges, understand the pressures they're after, understand the world that they live in, and so that we can better help them and deliver the services that are out there. We have 2 hours this afternoon to spend together, and in that 2 hours, we're going to cover a lot of material. We're going to kind of a look at application architectures in this client server versus the new modern microservice element as it goes in. And then you're going to join me on a bit of a journey. This session was actually originally developed to be used inside of Cisco to train our systems engineers and our solution architects to have this type of a conversation. Because as infrastructure and cloud applications and all these pieces started to become more popular and more important in organizations, we wanted our engineering teams to feel comfortable going and talking to application people, and so we needed to know their language. And so you're going to join me on a journey at how this content actually was developed and the corresponding application that we're going to use was developed as we tried to educate our systems engineers on that, and you're going to get the benefit of understanding kind of that same journey as we go through, because the message, I think, resonates really well for anybody that's in the infrastructure engineering space trying to relate to application folks that are out there. So the application we're going to talk about is we're actually going to start back at the early days of designing and building an MVP, a minimal viable product. We'll take a look at what it means to be a developer, what their tooling looks like, how they want to work, kind of what they're trying to approach and the things that they want that they're after. Microservices are made up of code that your developers write, as well as a bunch of building blocks that they pull into their application to solve certain problems. And we'll talk about those building blocks, but more importantly, we'll talk about the building blocks in relation to the problems that they solve for your application developers, and see why an application developer might bring one of these things like a caching service or a queuing service into their application. Once we've gotten through that, we'll talk about how the development process has changed a little bit from the traditional days of writing code and then manual integration engineers and development and packaging engineers into the land of continuous development and CI/CD and how that evolution has happened. And at the very end of the session, we'll come back to what it means to build and manage an infrastructure stack that can be used to deliver these types of applications. So we'll circle back to the infrastructure piece at the end. Now, through today's session, the goal is not in 2 hours to take all of you and turn you into software developers. So, you may not be interested in that. I, frankly, am not terribly interested in that piece. The point is to give you enough knowledge and context so that you can talk to the folks that are out there and relate to them better. And the whole reason we want to do that comes down to this fact that today, in organizations, applications are no longer just things that are used for back office functions. Manufacturing teams have applications that do manufacturing warehouses, and HR teams for human resource management, and accounting teams for those. But today, applications are also how we interact with our customers. They're defining the business, right? Defining so many organizations today are actually their application. Like you think about the big ones, like Facebook, right? Facebook is an application. That's what people interact with. That's all what it makes. There's all of the obvious ones, the Ubers, the Airbnbs that are out there. But many of our own organizations are starting to change their model. From airlines that view the only way that they interact with their customers are through their websites and their mobile apps, to banks that only really exist as a mobile application on somebody's, right? We're defining our business and our interaction with customers through the applications. And so if as infrastructure engineers, we want to continue to support these organizations where these applications mean differently, we need to become relevant and be able to fit into that dialogue. And that's why a session like today is important, is so we can help better understand the folks that we're supporting that are out there. Now we have a lot of content we're going to go through, so I'm going to start out by letting you know what my goals are for today's session, because there's a lot we're going to go through, but there's really only 3 main bullet points I'm hoping at the end of today's session, and we'll circle back to this, that you'll be able to kind of feel comfortable with. First, I want everybody at the end of today's session to be able to describe what a microservice application architecture looks like and how it differs and how it relates to a traditional client-server architecture and why some of the decisions are made. Secondly, I'm hoping everybody will come out of this and understand the common building blocks like containers, proxies, queues, and what aspect and what problems inside of our application development teams they're solving, and why somebody might want to use one of those as part of their application. And then lastly, why the traditional infrastructure platform, and in there I'm talking about like x86 virtualized data centers, aren't meeting the needs of modern applications and application development teams. With the idea being that you'll go back to work on Monday and you'll get called into your boss's office and he say, hey, I've got a meeting with the application development director and I have no idea about this microservice and this cloud native stuff that's going on. Can you help me out? And you can feel comfortable kind of briefing him and getting him ready for those meetings with the same type of areas. Like, that's the goal of today's session. Now, as I mentioned, our entire conversation is going to revolve around an actual application. It's called the My Hero application, and it's an application I wrote to go along with the content and actually educate myself. And it's a simple voting application that allows you to vote for your favorite on-screen superhero, and it's a microservice application that we're going to take a look at. And it's live on the internet, and if you join the WebEx Teams room for today's session, I put the link in there so that you can find it if you want to check the app out. But it's http://myhero.imapex.io will get you there. And then through today's session, we're going to see how this application came to be what it is and what you see it today, and we'll leverage several demos aligning to that application as it goes through. Speaking of the WebEx Teams room, we're a fairly small group in a small room. If you have a question during today's session, just raise a hand. We'll tackle them live. After today's session, feel free to use that WebEx Teams room to stay in touch if stuff comes up, if you're having trouble finding the slides, any of those pieces. You can use those rooms to communicate with me as we go through. All right, so let's dive in. Client-server versus a microservice application. I'm assuming everybody has heard of client-server applications, right? We know what those are, client-server. So let's start with what we know. A client-server application, often known as like web app data, or client-server database. These are traditional application architectures that have been around for a long time. Many applications in our organizations are designed and built in this way. We have characteristics at each part of this application, client, server, and database, that have determined how this architecture looks and why it fits well as it goes through. And so let's take them apart one piece at a time. So first, clients, the users of our application. These types of applications are built, and this architecture works best when you have a small number, or maybe not a small number, but a very well-known and understood set of users. So a lot of our client-server applications are those internal back-office applications that we've talked about. So manufacturing apps, HR apps, maybe if you're in a healthcare organization, the healthcare system where your doctors and nurses interact. Right? We know who our users are, how many there are. We know the type of device that they're going to connect to our application and use, because odds are good we gave them that device. Right? We know a lot about our clients. So that's our client base as it goes through. Then our server components. The server components are a small number of very complex components. And so if you think about these traditional client-server applications, this is where the concept of pets and cattle might pop up if you've heard that before. Our client-server applications are often made up of a series of virtual machines in this application tier or this business logic tier. Now, I worked at a healthcare organization. Our main application, we had about 4 that we would call kind of this application or server area. 4 different virtual machines, so a small number, but what each of those virtual machines did was a huge amount of processing pieces. On every one of those servers, there were dozens of different Java processes or C processes and executables, database transaction logic, transformation activities that go on. And so we have a small number of servers, but every one of them is doing a lot of things, right? The reason we tackle this is because our goal as operation engineers, like running an application like this, is to make our life as easy and simple as possible. Client-server applications are often kind of set up, and then they get basic maintenance as it goes through, but they don't get a lot of updates. And so we don't want to have to monitor hundreds of servers that are out there. We want to be able to target in on a small number of pieces, a small number of touch points. And when we have to do an upgrade, I don't want to have to log into hundreds of systems. I want to have a few of them that I go to, and we'll take a major downtime, a major maintenance window. We'll do those upgrades. These types of applications might get an update once or twice a year, right? It doesn't happen a lot, but everybody knows when it happens. We plan for months in advance. The emails go out that we're going to be down over this weekend, and the application analyst run the updates, they make sure everything's good, and eventually the applications come back up and we move right along. Like that's how these apps tend to be operated as they go through. Small number of touch points for our operations and application engineers, but each touch point does a lot. And if one of those servers goes down, everybody knows because it's so critical to how this application architecture works. So it's all hands on deck until those components come back. So that's our server layer, our application layer. That's what they look like. At the data layer, client-server applications always have some transactional database at the back end. Maybe it's a Microsoft SQL Server, or Oracle, or Postgres, or MySQL, but it's a big database that kind of houses all of the data for this application. Right? Traditional style client-server application. I would be surprised if you didn't have several of these in your organization today, and you may still be deploying more like that. Because that's the other key element about this, is client-server applications, this architecture still fits for lots of different apps. Like this isn't going away, right? We still have it. But there are other kinds of applications that tend to be our customer-facing apps, these things that are innovative elements of what we're after. And this is where the application teams and our DevOps teams and our lines of business are figuring out how to better build applications and be responsive to your customers that are out there. And so there are folks that advise your application teams on how to build these applications, because everybody's doing it. And so there's things like the 12-factor application, or 12factor.net, which is a series of, big shocker, 12 things that people say that if you're building a modern application today, these are things you should do, right? It's an opinion. Everybody has an opinion out there. And here are an opinion that came, frankly, from the folks at a company called Heroku. And they are a modern application platform as a service. And wouldn't you know it, that if you follow all 12 factors, a great place to build your application would be on their platform. Go figure. However, there's a lot of really good stuff in those 12 factors. And I guarantee your application developers have gone through that, and they understand the 12 factors. And they're considering that as they build their apps, even if they're not using Heroku. Because you can take those and use them as good, common sense ways to build an application. And here's what I challenge all of you to do. If you haven't read them yet, at some point on the plane home, log in, take a look at the 12 factors, read through them. It won't take that long. You probably won't understand all of the pieces that are there, because some of it is very specific to application development. But you'll understand the gist of how a lot of them go through. And you'll get an idea of kind of how modern applications are being thought about. And then if you go back and you talk to one of your application developers that are building your new modern web application or a mobile application, and you can say, hey, I was reading about this 12-factor app thing. Can you help me understand how our applications are aligning to that? You'll get a really interesting response from your application developers. A, they're going to be surprised you're interested in how the apps are going through, but also that you've looked at stuff that's relevant to their life. And down the road, if you're looking at an application that's out there and you notice that part of your new applications are violating one of the 12 factors, which happens quite regularly, but there's always a reason that they're violated. And so if you go back to that application developer and say, hey, I noticed that we're really not aligning to this in the 12 factors. Can you help me understand why? This is an interest level and understanding how it goes in, and you'll start to relate. And if any of you are starting to move kind of down that automation path yourself in the infrastructure space, a lot of the stuff in the 12 factors will relate to the own work you're doing as you're automating your infrastructure piece. There's some good stuff in there. Right? They're not perfect. It's an opinion, but it's an opinion that's very popular in the cloud native and the microservice application teams. Secondly, we have Conway's Law. Conway's Law loosely states that if you build an architecture for an application, your application architecture will look an awful lot like your HR organization. And so if you group all of your web developers on one team, and you group all of your middleware developers on one team, and all your database guys on one team, don't be surprised that your application architectures are web app data. It's just how things work. And so development teams and development leaders in HR organizations are using Conway's Law to mix teams together to help in this transition as they go through. So in application development teams, often you'll find a single team where you've got a web guy, a middleware guy, a data guy, maybe a security guy, all working together as they try to challenge some of the status quo on how applications are done. And then there are industry leaders like Werner Vogel. He's Amazon Cloud CTO, and they know a thing or two about building modern applications that are highly resilient and scalable as they go through. And Amazon is more than happy to give advice to application developers on how they can build their applications in that factor. So your application developers are taking in all of this and more information as they're designing your new applications. And so that leads to the microservice application architecture. And at first glance, this may look an awful lot like the client-server application architecture we saw. And I did that on purpose, because we can correlate what a client-server application looks like and why things have changed and how they differ in a microservice world. Let's take them one step at a time. From our client perspective, we now have an ever-changing number and type of users. Remember our traditional applications, we knew who our users were. We probably give them a paycheck and a laptop. These types of applications, our users are the customers. They're out in the world. We don't know who they are. We don't know what type of device they're going to come from. We don't know how many we'll have. Many organizations may launch some new application idea. Some skunkworks team came up with an idea for something that your organization could do. They launched some new application to the iOS and the Google Play Store. And then they're happy that they've got maybe a dozen or 24 people using the application. And they're ecstatic, and it's working great. And things are going along, so small number of users, they get some information. And then lo and behold, one of the users happens to be Ashton Kutcher, Justin Bieber, one of the Kardashians. And on a whimsy, they've decided that your application makes their life easier. And they tweet something about it. And overnight, not even overnight, like instantaneously, your 24 users blows up to 10,000, 100,000 users. So microservice applications have to be designed to be able to expand and contract and react to that successfully. Because there are two possible results after a viral tweet goes out about your brand new application. One is a good one. Things go well. Your application development team gets called up. The CEO is on why their stock just went through the skyrocket. Google is now offering $500 million to acquire your company. Things are great. That's if everything goes well. If it doesn't go well, nobody hears about your company. Right? Nobody knows what happened. These are the opportunities that application developers have to be ready for, because you have a split-second chance sometimes to be successful, and it comes down to how you interact with your clients. And not just the number of them, the types of devices. If you build your application and it only works if you're connecting from a Macintosh laptop, you've significantly limited your pool of users. You have to support laptops and desktops and smartphones and tablets and wearables and voice technology. And you have no idea what applications are installed along with those pieces. So we have no control over what our clients are. We have to build for that. It's a very different type of client base in this type of an application. Our users are coming to us over the cloud, over the internet, right? So they connect to us, and they get into what we now have as the microservice part of our application architecture. The microservice portion kind of replaces the old application or the server component of the architecture. And now, rather than a small number of complex components, we reverse it. We have a large number of very, very simple components. This is the microservice element. Now remember back to the client-server app. We wanted a small number of complex components because we wanted to make it easy for us to operate. Here, we have a large number of simple components because we want to make it easy for us to operate. Same end goal, but we have to do it differently. Because these types of applications are constantly changing. And when we change a microservice application, it can't take the entire application down. Right? Nobody wants a downtime window for Netflix. Right? It always has to work. And if there's a problem with one microservice, we need to be able to target and react to it without interfacing and causing problems on the other side. I guarantee you, there are times when some microservice at Netflix or Uber or Amazon or Google goes on the fritz. And overall, the application is fine. But maybe when you're on Netflix, you're getting a cached set of movie recommendations rather than a live recommendations list because the live recommendation service is currently down. You don't know. They react to that. They build their application around it. When that recommendation service needs to be updated, that team can target their microservice only without affecting everybody else that's out there. Right? This is what it means to operate a microservice layer in the application architecture. Simple components, but a lot of them. Now that brings in scale challenges, and we'll talk about how we handle some of those scale challenges, where we go from having maybe 3 or 4 critical servers for our application tier to having hundreds or thousands of Docker containers running someplace, right? How do we adjust our architecture to support that? The other thing that's interesting is in the current model, client-server app, we have all of these things, processes running on an application server, and they talk to each other on that same server. They use internal sockets to communicate with each other, database transaction calls, right? It all just happens on the box. In a microservice world, we have to have some sort of a communication bus, or message bus, or request layer. So these application services, these microservices can talk to each other. And this is where things like REST APIs come in. It also means the network becomes that much more important, because the network has to be live so that these microservices can talk to each other. And there are all sorts of new technologies and services and protocols that are being designed to help different microservices find each other and add in security and all these other pieces that go out. Entire elements of cloud-based networking targeted just at that type of a challenge. And not to leave out the data, right? In a traditional client-server app, web app data, right, we have a single transactional database, some gigantic SQL database someplace that is the back end. And we've got DBAs that like care and feed and run all sorts of maintenance on there, and transaction log shipping and cloning and all sorts of clustering to make sure that database is up, because the entire application relies on it. Microservice applications still have data, but instead of having a single transactional database, we have many sources, types, and locations of data. There may be, and likely will be, some relational transactional database that's part of the data tier for a microservice app, but there's also going to be big data, right? There's going to be all of those other Hadoop types of pieces and log information that's out there. One of the most interesting parts of the data tier for these applications is that the data may not actually be owned by you or your organization or in your control. Let's take an example of an application. We've got a startup application. We want to build an app to help the snowboarders and the skiers, as they're preparing for the Winter Olympics, find the best place to go. Like, where is the snow the best? Where are the hills the best? Where are they best groomed? Where are the X Games photographers so I can get really good shots in my air? Like, where do I go? That's my application I want to build. A key part of data that I need for my app is weather information. But I'm like any good startup guy. It's me in my garage, and I can't deploy weather stations across the entire globe. I don't have to today, right? We've got weather.com. We've got Weather Underground. We've got all of these services that can give me that data at a cost. I can subscribe and say, hey, I want weather information. And so now the most critical piece of data for my application isn't owned or under my control. I just get it as a service as it goes in. So we start pulling things in out of these other areas. So the data bit is a different piece as well. So every part of the application, the clients we work with, our application middleware layer, the types of data that's out there, the applications that are being built like this, they have just characteristics that mean they don't fit well into a client-server application architecture as we talked about. Now there are, as I mentioned before, there are applications being built today that still fit into client-server app, and they're built that way. But applications that are these characteristics, this is the direction folks go. When we build a microservice application, or really any application today, there will be code that your developers build, and then there will be services and building blocks that they bring into their application to help solve problems and challenges. So we'll have virtual machines that make up part of our applications. Yep, they still exist, right? We still do some of that even in modern applications. We'll have containers, and then the latest kid on the block, serverless. Nobody wants servers anymore, right? There's our databases, our proxies, our queues, caches. We're going to talk about every piece of this and what problems they solve and when an application developer brings them in. Because I'll let you in on a little secret. Your application developers don't want to use any of that. They want to make their application architecture as simple as possible with just the code that they need. They bring things like this in when they hit a problem, a roadblock, a challenge that they have to solve. And so we're going to see how these come into an application and the problems that they solve as it goes in. So with the groundwork laid, let's get into that demo application I talked about. And we're going to start with the birth of an application. This is where the MVP comes in, the minimal viable product. And I want to take you back in time with me to January of 2015. January of 2015 was an important time at Cisco in the cloud world, right? We had recently announced this concept of intercloud, where we were going to help connect clouds of cloud, build a federation. And we had a new product that was part of this intercloud strategy called Intercloud Fabric. And at that point, what Intercloud Fabric provided was a way for organizations to connect their private data centers, their private clouds, to different public clouds, and provide layer 2 adjacency, security, mobility between these clouds. Okay? This was hybrid cloud. Cisco, still today, but back then, we were talking a lot about hybrid cloud. And I was a solutions architect focused on data center and cloud solutions. And so I was being told, go talk about hybrid cloud with your customers, help them understand it, help solve these problems that are out there. And I looked at the products we had, and I looked at the demonstrations that we were offered, and I thought to myself, we need something better than a Hello World demo. When Intercloud Fabric was first brought out, the demos that the business units, the developers gave us was a really boring demo. Right? They would spin something up, and we would open a web page, and it was a little cloud, and it said, hello world. Like, that's all it was. And under the hood, they said, yeah, we moved this around. It did all this magic. And I was like, that's terrible. It was a terrible demonstration. And so I sat down. I said, I think I can do better. And so that was where I started to go after the minimal viable product for my hero. And so according to Eric Ries, who's a big name in the startup culture, the microservice, the modern applications, is a minimal viable product says you have an idea, something that you think has merit. Now, the traditional way of building applications is you would go find a pile of money someplace, and you'd go secretly for about 5 years, build some application, get it exactly the way you wanted it. You would launch it and hope people would buy it and send you money. We've seen that doesn't always work really well. And so we turn it up on its head a little bit with the MVP. Now it says, you've got an idea, build the smallest version of that idea with the least amount of money, resources, and effort you can, and put it out into the market and see if people are actually interested. Right? Then if there's interest, now we start to invest, we get investors, we put effort into it, and we evolve it as it goes through. So a different structure. And so the My Hero MVP for the application looked like this. Very different than what it is today. It was a simple web application with a black and white text-based interface where radio buttons that would let you vote for superheroes. And it was designed at this point to go along with Intercloud Fabric. So it was deployed as virtual machines. And the way we deployed it is in the private cloud, the data layer. Remember, this is a client-server data. So the data tier would be in your private data center, because we want to secure that data. But the application and the web tiers, we would put out in the public cloud all over the world close to our users. So it would be fast and responsive. Okay? From an application architecture perspective, it was very much a web app data structure. Very traditional client-server. It deployed into virtual machines, and I could deploy it to the cloud. That was its entire purpose. So we did deploy it to the cloud, but it was not cloud native. It was not built around microservices, and it was definitely not DevOpsy. Like, it was very old school. That was the MVP. And I launched it, and I started using it for some of my demonstrations, and it went out. And it worked well for me, right? It gave me something to talk about. It showed how the technology worked. And I let other folks know that it was out there. I did a couple of webinars and let other coworkers know that it was there and said, hey, if you're doing a demo, have this. But it was still MVP status. I didn't know if there was really a reason for this. It worked fine for me. That was enough. I knew that I had something when it was about 3 a.m. I'm from Ohio, here in the States. It's about 3 a.m., and my phone rang, and my wife slapped me. Get the phone. And so I groggily woke up, grabbed my phone, went out into the hallway, and it was a technical marketing engineer. These are the TMEs on a Cisco team for Intercloud Fabric, and they were on site in Melbourne for Cisco Live Melbourne on the show floor, the World of Solutions floor for Intercloud Fabric, trying to use my demonstration app because they liked it better than their little Hello World app. And so I helped them, right? It was 3 a.m. I wanted to make sure it was successful, so I logged in, we walked them through, got it installed, it was great, worked fantastic for them. But I came out of that realizing that there was a market. There was a user's base for my application. I wasn't going to get millions of dollars for it, but other people wanted to use the app. And so I moved out of the MVP stage into an actual application. And so now we get into what happens after the MVP for a developer. So I come out of this and I've got, all right, we got to move forward. Time continues to go. What cloud means to Cisco, what cloud means to organizations change. Microservices start to evolve more than this kind of virtual machine-based structure. And so I set some targets for where I wanted to get to. Right? And so these are some elements and some key goals that we wanted to take My Hero MVP and move into the future. The first one is it needed to be easy to deploy. I wanted anybody to be able to deploy the demonstration without having to call me on the phone at 3 a.m. Right? That was number one priority. Number one priority. Anybody should do it. So that was the first thing I tackled. And my goal really was to be able to get on a WebEx, do a demonstration for my coworkers. And we set it up, and my boss thought I was going to show how easy it was to install. And I turned it on its head, and I said, no, you're going to install it with no warning. And I said, if I can get you to do it with no warning, I think we're good. And he successfully was able to install it, worked great. So I was, all right, easy to deploy. Needed to go containerized. Right? As time went on, moving from virtual machines to containers was the world. So we had to take this virtual machine-based application, wrap it up in some containers. So that was a step we had to take. Microservices. Along with containers, we wanted to get away from Intercloud Fabric. It was a great product, solved some specific challenges, but those challenges kind of aren't as big of a deal anymore because we get into the containerization world, the microservice world. And so we wanted to take the app and move it into a microservice-based application. Right? Go from client server to a microservice architecture, and we'll see what that meant and the evolution went in. A better web UI. Right? The original web UI was boring. It worked, but it was boring. So I wanted something a little nicer, so that's the modern web UI that we went in, using modern tooling that was out there. Auto scaling. We're going to talk a lot about where this comes in, but as the application went out, I wanted to make sure that those users, if I had more users, it would scale up and be able to respond effectively based on the size of the demo. So tackle auto scaling. Bots. Bots are still cool, but when I started doing this evolution, bots were really cool. Like everybody needed a bot, right? We had chat bots for toasters and washing machines and all of these pieces. And so I said, all right, let's add some bots. Right? I wanted to interact with my application in a different interface, not just a web page. And then lastly, the entire application in this presentation was designed to be an educational tool. So I wanted OK code. All of this code is publicly up on GitHub, everything from the MVP to its current status and the different pieces that are there. And if folks were going to look at it, I wanted people to understand what was going on. It's not supposed to be a production application. It's just supposed to be OK code. That was my goal. So I set out to solve these problems, and you're going to follow me on the journey as I challenge these problems, and then new ones started to come up. So my first step was to take off my infrastructure hat, get into the idea of an application developer, and the first place an application developer lives, right? Everything that they do comes down to source control and code repositories. Git is a system of version control, a mechanism that software developers can track changes to all of their code and the requisite files that make up their application. Git isn't the only code repository system or version control system, but it is the most popular one today. And it's a distributed version control system because most application development teams today are made up of more than one person. Right? And so we have different developers, developer 1, developer 2, developer 3. Each developer needs an instance, an entire version of the application. We'll call that the repository on their laptop. But they need to be able to work across each other. And so we have a distributed, a remote version of the repository that everybody can talk to. And so when I'm working locally and I make some changes, I can commit those and push them up to the remote repository. And then all the other developers can pull the changes local to themselves. This is how Git works. It allows developers to work on the same type of files or the same project, the same piece that's there, and stay in sync very easily. How many people still track like Visio diagrams or Excel spreadsheets with like .v1, .v2, .v3? This solves that problem, right? Make it much easier. Know who made changes, when they were changed, why they were changed. Now, repository structure comes into code projects. And so everything having to do with that application or that service should be inside of the repository. So this includes the code, the issues, the releases, documentation. All goes into the code repo, all goes into the source control. And now a single application may have more than one repo, right? And so in the case of the My Hero application, you can see here there are several repos that correspond to the overall My Hero application. The Spark, WebEx Teams, formerly known as Spark, this repo is still called Spark. All of the things to do with the Spark bot or the Teams bot live in that repo. Everything to do with the data live in that repo. This is the way that I chose to structure them. Some application teams say, okay, we'll have one repo for the full application and then a folder underneath it per service. Right? There's different ways to do it, but everything about the service, everything about that application lives inside of the repository. So that was the first step. Get the code, put where it needed to be. After that, I wanted to tackle the containerization, move from VMs to containers. So an application container is a way to wrap up everything necessary to run whatever the developer's code is, and nothing more than what's necessary to run the code, and make it a portable package as it goes in. Now, the most common container technology today is Docker. It's used in a lot of places, but it's not the only one, and it certainly wasn't the first. There's Linux containers, there's Rocket containers, but clearly Docker is leading the area here, and so that's what I went after for this solution. Now, you'll end up with a Docker container, or more specifically, a Docker image for every service that's part of your application. And so you'll see here I've got Docker images for the Tropo, the app, the data, the web. All of the pieces that make up the application, every one of them is a Docker image that I can use to run containers that are out there. The Docker file is the definition of what makes up the image, and it's very infrastructure as code fashion, and we'll see an example of that in a moment. Now, a point here is containers can make your life easier, but they don't automatically make your life easier. To build a Docker image, frankly, to build the Docker file, you need to understand your application and all of its dependencies and everything necessary to run that part of your application very, very, very well. Because there's no, oh, I forgot to do this, I'll go in and make this quick change, or I'll tweak this, and now the application's working. Everything has to be articulated up front in the Docker file exactly as needed. And so if you're an application developer starting a brand new project, that's usually easy because you're starting from scratch. You know where it goes in. But if you're trying to port an older application, a legacy component, into a Docker image, into a Docker container, it can be very, very complicated. If you're looking for a practical example, you can go find the Docker file, which is the definition for something like a MySQL database server, and just look at how complex it is for them to just automatically Dockerize something that's been around for so long, and then compare that to like the Docker file for a modern database like Mongo. Much simpler as they go in. I was lucky because there wasn't a lot that went into the MyHero application, but I did have to do that porting myself. Now, a Docker file, the way it works is every line in the file becomes a layer in the image, and we build from a known starting point. And so we can see from Nginx. So my web UI runs on Nginx. It's a common web server. Right? I could figure out how to configure and install and set up Nginx myself. We've got people that know how to do that. But it was much easier for me to say, you know what? The Nginx guys know really well how to set up an Nginx server. I'll just borrow from what they've done. So I can build on top of layers that other people have gone through. So you'll find source images for all sorts of different places where you can build right on top of them. And then maintainer, expose, copy, run, those are all additional layers building up what it is that makes up the image file. This is easier to see sometimes in an animation. And so we start out our Docker image with our base. Where are we going to start from? And so we had from Nginx. And then every line in the Docker file adds another layer on top of that. It's like a cake. And so the next one comes in and I say, okay, I'm going to stamp it. This new version is owned by Hank. And then after that, this is going to be a web server. So I need to expose port 80. So that's another layer on the Docker file. And then I install all the dependencies for my application. If this is a Python application, the dependencies are all of the pip install things I have to do. If it's a Java application or a JavaScript, it's all the npm installs. It's everything my application relies on that I didn't write myself. Those are the dependencies. Those all get put in as a layer. After that, I put my code in. Okay? I add my code, and then finally, I give the command what it takes to run it. So when I start up a version of this image as a container, how do I run the application? And then that gives me my built image. Once I have built all of those, over time, as I update my application, I can update the image file. The order of the layers and how this is built is very... Because when I make a change to a layer, everything of that layer and a thrown away and completely recreated. And so if we look at the order here, if I change my code, the only thing I have to get rid of is my code and then whatever the command is to run the application. That's not a lot. But if I added my code to the image right after the base, every time I updated my code, I'd have to rebuild the entire image file, which is a slow process. And when in some application teams, they try to cut new releases multiple times a day, efficiency becomes really important as it goes in. Okay? So the construction of these Docker images and how they're built, the order that goes in, very important piece. Someone on the application development team is like, that's their expertise, is figuring out the most efficient way to build these as they go in. Now, a quick sidebar about application environments. One of the 12 factors says that we need to disconnect our application code from the configuration information about our application. And so the idea here is, the goal is that I should be able to take something like a Docker image and run that in the same exact image in dev and test and QA, and somebody else goes through. Everybody should use the exact same code, but the details about that instance of that application might change. So the passwords that are used for the APIs to interact with each other. If this microservice is the API layer, right, it has to talk to a data layer. So the address for the data layer might change between different instances of the application. So we need a way to inject that. And that's all called environment configuration, things that change the environment. And the way that's often done with microservice applications is the use of environment variables. Environment variables exist on every modern operating system, and it's a way to specify variables with values. And so when your Docker container starts up, your code says, go find the value for the MyHero app server, and it asks the environment variable and it uses it. So that doesn't have to be buried into the code. Has anybody had the challenge of having a hard-coded IP address someplace in somebody's code, and then you can never change that IP address? Right? It's things like that we're trying to solve in some of these new architectures as we go through. Now, the development environment is the next thing I want to talk about. The development environment is really the working environment, the tools, the laptop, the setup that your application developers want to work through. And a development environment is a very personal experience for every application developer. They're going to have their preferred platform. Are they a Mac or a Linux or a Windows guy? Are they a Vim or an Emacs, right? What are the tools that they like to use? What are the platforms they want to go through to make themselves feel comfortable and more efficient? All of that goes into the development environment that goes in. Now, many organizations, many development teams are trying to provide flexibility to their developers so that they can be very custom in what they're after. And then we provide tools like Vagrant that allow every developer to have independence in what their development environment is, but have everybody also still be consistent in how they develop their app. And so what Vagrant is it's one example. It's an open source tool by a company called HashiCorp, which is they build a lot of tools for application developers. And it's a way to define and package up what it means to run a development instance of an application in a way that can be included in the code repository. So every developer can very easily spin up an exact replica of the environment, do their coding, and it's isolated from whatever dependencies and whatever's unique about their own laptop as it goes in. So with the MyHero application, I've included what's called the Vagrant file in every repository. And that is what Vagrant uses to understand and describe how we set up the development environment. You can think of it like a Docker file, right? It's a definition of how to set up that part of the application as it goes in. And the goal here is that anybody, including all of you, if you have Vagrant and Docker installed on your laptop, is that you would be able to clone down the repository and then immediately just type Vagrant up, and it would bring up the application as it goes in. And Vagrant works alongside things like Docker and VirtualBox and vCenter to host these applications that are there. So I've been talking for about 45 minutes, so let's jump off to our first demo and kind of see how some of these pieces go together that's in there. All right, switch over here. All right, is that text big enough for the folks in the back? Yeah, okay. So what we've got here is this is a Vagrant file, I think for the data tier. Yep, for the data tier for the application. So what you can see is it's a text file that's very easy to read. And we can see down here the provider, so the technology that's going to be used to build my development environment will be Docker. And then I simply give it where to find the Docker file for this application. Dot indicates current directory. So the Docker file is in the same place the Vagrant file is. I specify any ports that are used. So this application typically runs on port 5000, but in the development instance, we're going to run port 15,000. And then a few environment variables to determine how this instance of the application will work. And so data, app, UI, they all have the Vagrant files. And then in the repository is the Docker file. And so here's the Docker file for the data tier. And you can see it's fairly simple. So we expose port 5000, I stamp it with my information, create a volume here called app data where we'll put all the app pieces that are there. I use APK, which is just, it's like yum or apt to go ahead and install some dependencies that are needed. I add in the code for my application, and then we do some installation. And this is how we actually run the data tier of this application. So that's the Docker file. And I've already done the Vagrant up over here for the data tier. So Vagrant status will show that I indeed have, it's running, and it's running in Docker as it goes through. And I can go through here and I can do the same thing for the application tier. So Vagrant status. And so these are just three terminals all for my laptop. So same environment, just different parts of the app. So this is the app, we can see it's running. And so I can actually go through and send a curl statement here. You can see I'm sending a curl statement to localhost, so my laptop, port 15001, that's the application service and development. And I'm asking for the different options. Who can we vote for? And so if I send that, I can see it returns back and gives me all of the options that are there. So I can interact with this. So if I was working on the application tier, it's all running locally right on my laptop. And if I wanted to work on the UI tier, I can go ahead and say Vagrant up in the UI folder, and I didn't up it before the demo. And you can see here where it's building an instance of the image and then immediately starting the container that quickly. And so now if I go over to Chrome, we can see that I can open up localhost and then 15080, I think is the port. Yep. And so this is an instance of the entire application that's tied to the application and the data tier right on my laptop. And so if I was working on the UI, I could go ahead and manipulate this. So I could place votes that are out there. I can go ahead and just see that the app is working. And I can use the tooling that's there. So my entire application is now running as an instance, a development environment instance right on my laptop. So as a developer, I can do this from anywhere. I can do this from the office in my cube. I can do this from Starbucks. I can do this from a plane. Right? That portability as a developer is really important to me. I don't want to be chained to some boring cubicle. We want to have that ability. And that development environment is a big part of what it means to be a developer today, making it portable. DevOps is a huge part of development today. And it used to be, and maybe still in some organizations, a developer might say, you know what, the application worked fine when I ran it on my laptop that's heavily customized and tweaked and all of these things go through. I don't care, it's your problem, you go figure it out. The whole like DevOps like challenge that's there. With the mindset of DevOps, now the developers are a little bit more on the hook to make sure that things actually work in operations as we're trying to connect them together. And so tools like Vagrant didn't come out because developers didn't like being able to just run them the way they liked it. What they needed was a way to very easily and repeatably replicate as close to production as possible the entire application, and so that they could test it in a way that kind of would look and act when it was in production. So they wouldn't have as many differences between the two different locations. And so these types of tools came in, and so that they could have that consistency. And today that's the goal, is that when I run an application in development on my laptop dedicated just for me, it is as close as possible to the exact same application, the same platforms, the same dependencies, the same interactions, as what it is when it's in production, where it might be running on a big Kubernetes cluster or running in a public cloud or private cloud. That's always the goal. Get as much consistency as we can, and tools like Vagrant try to help us do that. All right. So moving along, so at this point in the strategy, what I've done is I've taken what was originally a client-server application, I containerized it, I added a little bit of development environment around it, made it a little bit better, but at this point it was basically the exact same application, right? It was still that ugly client-server or client web, and it was still very much client-server. There wasn't a lot of extra pieces put in. And I started to get asked to go talk about this application at things like what we call at Cisco the SEVTs. They're biannual SE meetings where we come together as an organization and we learn from the BUs what's coming out, we learn from each other about best practices, and it's a time to go through. And so folks I'd known, I was working on this, and said, why don't you come talk to your fellow SEs and explain some of what you're doing and what you've learned, and we can start to go out. And so I went and I did this first demonstration, and I was super excited to have a chance to talk at an SEVT. And my SGMs in the back, I think we're probably both at that first SEVT, where I did this demonstration. And I went up and I talked about it, and I got introduced, and I put the URL up, very similar to what I did with you guys. And I said, that's my application, go try it out. And it lasted about 4.5 seconds before the entire application just crashed completely. Like it just stopped working. And I got a little red in the face, a little bit embarrassed. But I went through and did the presentation, still talked about like what I'd learned and what I'd gone through. And then I went back to try to figure out what went wrong. The app had been working fine. I'd been using it, I tested it, I tossed the link to a few other folks, like everything was good. But I learned that it's very different to have an application that you're just playing and developing and testing yourself than putting it out there for other people to use. And this is where my supporting cast comes in, where all these microservice elements start to factor into the application. And so I started doing some research coming out of that SEVT because I knew I was going to get a chance to go back and do better. And so I looked at it, and very quickly I realized what the problem was. That first version of the application had one web server, and it wasn't a very good web server. And so having everybody, hundreds of people, try to hit the same web server at once, it just couldn't keep up. This is a problem we've known in the networking space and in application space for a long time. How do we fix it? We fix it with load balancing. Right? So I needed to add load balancing to my application. In the microservice world, we talk about load balancing and proxying together. And so here's some definitions from Wikipedia. Load balancing improves the distribution of workloads across multiple computing resources, while reverse proxies is a type of proxy server that retrieves resources on behalf of the client from one or more servers. It took me a really long time to admit the fact that I had no idea what those meant and how they differed. And so I did some research, tried to figure out exactly how they actually interact, what the difference between load balancers and proxies are, and I came up with my own definitions that I think are more realistic and kind of explain how these go together. Load balancers it's a simple function of distributing the request across a set of systems. So I get a request in for a web page and say, okay, you go here, you go here, you go here. Very simple, just distribution mechanism. Reverse proxies add additional features on top of it. Things like SSL offload, or cookie rewrites, acceleration features. So frankly, most things we think of as a load balancer today are actually combining together the features of load balancing and reverse proxies, which is why they're often pulled together as they go in. Now organizations today, I guarantee all of you probably have some load balancer reverse proxy in your environment. F5, A10, Citrix, like there's all these guys that are there. But in the modern application, the cloud-native application space, things are a bit different in the requirements from the load balancers and proxies. Because we don't have maybe 4 or 5 web servers we're load balancing. We might have hundreds of them. And these things may change all the time. Many organizations, if I need to add a new server into a pool, I open up a ticket, it goes into a queue, a couple of days later, maybe somebody goes ahead and actually makes the change that's there. Remember back to the start, somebody sent a tweet out about our application, and automatically we need to be able to scale up to react to that. We can't wait for a help desk ticket to be responded to. And so modern application platforms are leveraging tools like Trafic or Nginx and HA Proxy. These are other solutions that offer interaction with the underlying infrastructure platforms running these Docker containers and these images and these workloads. And so as soon as the workload scales up, the load balancing and the reverse proxies automatically scale up and down on demand. And they offer capabilities to load balance based on layer 7 information, like the URL, and not just the IP addresses and the ports as they go through. And so I got lucky. Most microservice platforms you leverage, be it Kubernetes or Docker Swarm or something like Mesosphere that's out there, actually offer something typically called like an ingress service that can automatically provide load balancing and proxy services to the applications that are out there. And so once I containerized the application and then deployed it onto a microservice platform, I didn't have to do anything extra because the platform kind of delivered me load balancing and proxy services automatically. And here's a quick snapshot from a Kubernetes cluster where we can see I'm describing the ingress service for my hero. And we can see the API, the Spark, and the My Hero, the actual web app, are all being provided. And they're being done based on the URLs. And so if somebody goes to myhero.imapex.io, it will send it over to the MyHero UI service on port 80. Same IP address, it's blocked out on the slide, but if you go to Spark, the DNS name resolves to the same IP, but because it's a different URL, a different host entry, it sends it to a different service. So layer 7 load balancing, built into most of the microservice platforms, and your application developers just expect this to work. Application developers are not going to open up tickets anymore when they want to scale up a container. It's not going to happen. It needs to be part of what's out there. And so I deployed to a microservice platform, I got this capability, and the new architecture for the My Hero app looked like this at this point in time. All of the application and the web and the data tiers had all been containerized, and I wanted to be ready for my next demonstration. So at the web layer and the application layer, I scaled up to dozens of instances. I was not going to have the problem where my web servers crashed anymore. But the application is still very client-server-ish with the data, so my data tier, I only had one container because I couldn't actually scale that up. Like, it's not a scalable data tier, so I'm still stuck with just the one data tier at this point. But I'm like, I'm probably okay, right? I've got hundreds of web servers. I got hundreds of API servers. Clearly, I'll be able to keep up with it. And so several months later, I got a chance to present to some more SEs, same type of a thing, give them the URL. I say, hey, go try it out. Remember, the first time it lasted 4.5, 5 seconds. This time I made it all of like 7 seconds, and it crashed again. Like, just flames. I was like, what the heck? Like, I could not have given it more web servers or API servers. What's the problem? Why can't I keep up with it? And so my next challenge should be fairly obvious. Like, I kind of hinted at it. I've got one data tier. And so if we look at the architecture, when somebody comes into this system and they want to place a vote, they get the web server, and I got lots of those. The web server makes a request off to the API layer. I got lots of those. But the API layer still needs to record that vote into the data tier. There's only one of those. And so that was where my problem was, is I was just overloading the data system with the requests that came in. I couldn't load balance this. The application didn't support me just saying, I'll have lots of data servers. I needed something else to go through. And so I go back to those building blocks we talked about. And I said, there's got to be something. I can't be the first application developer to have this problem. And I wasn't. Message queuing systems solve these types of problems. A message queue for an application developer provides a capability for asynchronous communication. This allows for part of an application to run at one speed, while other parts of the application run at another speed. Right? We don't have to run the entire app at the same speed. And so we can go ahead and make requests of another system, and that system can respond to those as fast as they can at the rate that they're comfortable with. And this allows the services to become resilient and both independent. Right? We don't have to rely on how fast the data tier works for my application tier to be functional. So it supports things like bursty patterns and slow processes. And so the idea behind a message queue, and MQTT is a protocol for message queuing, is that I have clients and I have servers. And clients are my requests, things that I need my servers to do. And so the clients push to a queue all of the work that needs to be done. And says, hey, I need somebody to do this job. And it just piles up in a queue. And then all of your servers subscribe to the queue, and then as fast as they can, they just take the next element of the queue and process that job. And then they may send something back into the queue about the response. Like, I did this job, everything's good. And so we can constantly run at different speeds that are there. This is what I needed. I needed a way to be able to send votes as fast as the votes came in and have the data tier be able to respond to it. And so when I thought about it from a voting application perspective, if we go in to vote at a polling station, right, we place our votes depending on where you are in the world or even here in the US, different systems are there. But in my county, when I vote, I fill out the paper, I walk up to a machine, and I slide it in. And I don't sit there and wait for my vote to be registered by like CNN and Fox News. Like, I count on the fact that it will actually get counted. We hope. Right? So slide it in the machine, and I walk out on my merry way knowing that at some point it'll be officially counted. I said, if that works for like big elections, it should work for me. And so here we said, okay, I'm going to go through, and out of the application tier, I'm going to publish votes as they come in into a system called My Hero Mosca. So it's a new microservice that's going to go into the application architecture. That is the queue. All the votes get just pushed into Mosca. And then I needed a system that could actually count those votes and record them into the data tier. And so a new service was designed called My Hero Ernst. So it's called My Hero Ernst because here in the States, all of the big awards ceremonies, the organization of Ernst & Young are the accountants that count the votes for the Oscars and everybody else. And I figured if it was good enough for them, Ernst was good enough for me. And so My Hero Ernst counts those votes as quickly at the pace that it can and then send them into the data. So we rate limit going into the data system. Right? I had to add additional code for Ernst. I wrote that. I didn't want to. If I wanted to, I would have done it up front, but I had to do it. Mosca, I didn't write that. That's an open source queuing system that was already available out there. I didn't have to write it. I could have, but if I wrote my own queuing system, that would add no additional value to my application. It would burn development cycles. This is where the open source and these building blocks come in, as I'm like, I need a queue. Someone already built one. Great, I will use that queue. And this is how your developers think too. I need something to solve this problem. It doesn't add any differentiation to our application. It's just a service I need. I want to go grab it, and I just want to use it. Make it easy. Right? So this adds some complexity, but it buffers for all these votes coming into the data. I'm like, all right, I'm feeling pretty good. Now I can rate limit the votes as they come in. Don't have to worry about it. Have another shot to do a demonstration. All right, first time, 5-ish seconds. Second time, like 7 seconds. I'm like, this has got to do it, right? I'm rate limiting, I'm protecting with what's out there. I do my demonstration, and I think I lasted about maybe a dozen, 20 seconds before the application crashed again. I was like, come on. Like, really? I was getting a little bit embarrassed at this point because I kept coming back thinking I had it. Everybody's laughing at me a bit, but they're all my coworkers. It's all in good fun as it goes in. And I'm like, all right, so we go through, I do the presentation, we do the demo, crash, I go look at it. I'm like, what's left? Well, at this point, right, the queuing solves my vote problem, but anytime somebody wants the results or anybody needs the options list, like who they can vote for, that's still a direct hook from the application to the data tier. And this was my bottleneck, my next bottleneck I found, is that every time somebody went to the web page and it had to display the results, it had to go ask the data, what are the results, and it would calculate them and it would put it up. Every time I wanted the options list, I'd have to go to the data tier. Right? So I had another problem. Queuing doesn't solve this. When I need the results information or I need the options, I need it now. I can't wait for it. So asynchronous doesn't solve this. Go back to the building blocks, I figure out what's out there in my toolkit, and this is where I discovered caching services. Caching services aren't terribly new. We've seen them all over the place that's out there. And they're used everywhere from the hardware on our computers all the way into application systems. And it's a mechanism to speed up systems by providing data that's needed closer to where it's needed, right? Taking it out of one storage, putting it someplace else. That's the whole idea behind a cache. And so inside of our cache here, what we end up with is we've got the idea that I've got clients and I've got a web server. Now this is not the My Hero cache, but this is a common use case where I've got a web server and I just cache at the edge the data that's needed. A good example for this is when all of the big iOS updates go to phones or computers, right? They all eventually have to go back someplace to Apple. But the Akamai systems actually cache all of those things around the world so that when you're downloading these services, you're not waiting to go back to Apple for all of those or to wherever your provider is. You're going to get it from some closer cache that's out there. And so I thought about this. Is there a way that I can apply caching to solve my current problem? As an application developer, again, I didn't want to add anything new, but I needed to. My app wasn't working. And so when I thought about it, the voting options rarely change. In fact, since I've developed the application, the voting options really haven't changed at all. So the options are always what the options are. And then from a results perspective, care or even know if the voting result data that's displayed on the web page isn't up to the minute accurate. Right? I guarantee most of the times when we get voting results like on the news, it's not up to the minute accurate either. And so I said, what if we go ahead and say, okay, every time someone requests the voting options, right, we save it. We save it for 5 minutes. Right? We don't ask, if we've asked in the last 5 minutes, don't get new options. And from a results perspective, if I'm asking for the results and I've had them in less than a minute ago, just give the results back. Don't ask for the newest ones. And so there's different ways to apply caching. I did this simply in the application architecture, and just at the application layer, the API layer, I just said, go hold on to it here. Don't ask for it if you've asked for it recently. And the way you can see this is in the actual API calls. So this comes back from these are the response calls from the API tier, HTTP 1.1 200 OK, and we can see the date of the request. In this case, when I grabbed it, was Tuesday, January 2nd, 1543 GMT. The data timestamp shows when the data was from, and you can see that the data timestamp is a bit older than when the request was made. So I just add a little bit of delay, save it, cache it for a little bit. So my application architecture changes, not a lot in a picture, because as I mentioned, the caching is all implemented at this My Hero app layer. I'm just at that piece. Now there are systems like memcached and these things that are actual full caching services that real applications often deploy, right, as independent services. But for me, it was simple enough just to put it in the application tier. And so now my caching kind of gives me a buffering zone here. Everything that I've done was to protect the fact that my data layer was fragile, right? So I had to put this in place. I went back. I think it had been a year since I did the first demonstration for my SEs. I was back, and at this time it was the Cloud SEVT, talking about cloud-native applications, all the stuff that I'd learned. And I got up in front of the audience again. I'd been introduced. These guys have all seen me do this before. They're all waiting for me to crash and burn, right? They know it's coming. They know it's coming. And I'm very cautious, right? I did not expect it to work. I expected another example of every other one as it went through. So I got up on the stage. I was in San Jose. I remember the day because it was an important day. I think they remember, Eric and Greg probably remember it because they were there as well. And I get up on the stage, and I start the presentation. And I'm the session before lunch. So it's me and then lunch. I'm doing the presentation. I'm going through talking about the stuff I learned, what I'd adjusted to the application, how it went in. And I'm just waiting for like one of the demos to crash or somebody to be like, it's down. And I'm 5 minutes into it, and it seems okay. And I'm feeling pretty good. 10 minutes into it, still feeling pretty good. Things are pretty good. Hasn't crashed yet. And then I start to see around the room little laughter popping up. I'm like, what is going on? And there's laughter over here, and there's laughter over here. And I go and check the results, and I find out my app hadn't crashed. That was good. But a little war had broken out in the room. There was a Cisco SE up in like the upper right corner of the room who was a big Wonder Woman fan. And so he wanted Wonder Woman to win, so he was voting for Wonder Woman. And there were like 4 other SEs that wanted anybody other than Wonder Woman, not because it was Wonder Woman, but because they just didn't want Guillaume to win. That was it. And so they're trying to vote for other people. And so they're just sending votes in to go through. And this is the cloud, the automation set of SEs. And so these are guys that know a little bit of coding. And so they got to the point where they couldn't like click fast enough. And so they started to write some scripts, right? And so Guillaume wrote a script to vote for Wonder Woman. And it's running on his Mac. The other guys are writing theirs. I don't know what Guillaume was doing, but they couldn't keep up with him. And so this group of SEs happened to work for one of our cloud organizations inside Cisco. So they went to the cloud. They actually wrote My Hero Voter. It's another service, it's a little Python application. And they deployed it to the cloud. And they started to vote more. And then they deployed it to AWS, and they started to vote some more. And Guillaume was keeping up with it. Application never crashed through the entire session. It was great. I felt really proud, vindicated at the end of it. I'd done the work that was there. We went off to lunch. We're sitting at lunch. I'm sitting with the SEs, and my phone rings. I was like, that's weird. It's a Cisco IT. So I answer the phone, and they're like, your lab is under a DDoS attack. I'm like, what? Like, your lab, because this application was running out of a Cisco SE lab in Richfield, Ohio. It's where I worked out of. Your lab is under a DDoS attack. We're about to shut your entire lab down. I was like, no, don't do that. I explained, I'm at an SEVT. I'm doing a demonstration. I believe some of my coworkers might have gotten a little excited. I'll take care of it. So I frantically run around the lunchroom, and I ask Guillaume and all the rest of the guys to like turn their voter bots off to go through. And they did, and they didn't shut my lab down. At the end of it, we finish up, we go back to lunch, and I go check the stats. This application had held up through an hour of the most abuse it had seen. They'd gone to the cloud. They'd done the voting, AWS, OpenStack, lots of stuff engaged. And I went and looked at the results. Wonder Woman did win that day. I was very proud. I was happy for Guillaume. Wonder Woman won with 475,686 votes. I didn't catch what all the other ones were, but nobody had more. I think if everybody had piled up and voted for the same person, they probably could have, but the other ones, like, they distributed as it went through. And so over the course of that hour and the lunch break, my system had taken well over 2 million votes had come through in about an hour. And it had held up. It held up like a champ. It was still going. I don't know what the breaking point would have been. Breaking point was Cisco DDoS. That was the issue that came through. Now, I go through all of that because there's a lesson to be learned here. You followed me on my journey of solving load balancing, queuing, and then caching. And at that point, the application was solid, right? I wouldn't release it to like the internet, but it held up. All along the way, the actual code, right, everything we did was to protect like the data tier. This data layer held up for all of that punishment with very simple pieces, a little bit of queuing, a little bit of caching, and that data tier to this day is not Postgres, it's not a SQL, it's not MySQL, it is a text file. When you place a vote in this, it simply appends another line to the end of a text file. When I have to count the votes, the application tier gets the entire contents of the text file and then like calculates and counts as it goes through. It is very, very crappy code. It's a very crappy application, but a little bit of open source logic and business went in here, protected my application enough to keep up with it. That's how your application developers work. They're probably not quite as crappy as my architecture was, but it's the same general idea. They write parts of their code, they figure out what works, and then they start solving problems as they pop up, using these different building blocks to solve the challenges that are necessary. Nobody brings in a queuing service because they think it's an awesome idea, unless you happen to work for a queuing company, right? Nobody wants to put in extra complexity into their architecture. You bring it in because you need it to solve some problem, to protect your application. Keep your application code as tight, as best as it can. Leverage the other tools that you need to as it goes in. These are why these building blocks are used. So we've gone through load balancing, proxies, queuing, cache. At that point, my application was stable, but there are other things that we can talk about with modern applications. The next one we're going to hit is object storage. Now, we store things all over the place in IT. We store files, we store images, we store movies, we store all these things. We store on disk, or we store on file and block storage. Object storage is like another type of that. It's not file, it's not block, it's object storage, where we deal with some object, a picture, a file, a text file, a movie. And object storage is heavily used in cloud applications. And there's some characteristics of object storage. You access an object store typically through an HTTP URL. So it's a REST API-based access. Like every object that's in there, normally we go to a file path, right? C:/users, whatever. We access a file out of object storage by going to http:// and then some name. Like that's how we get objects out of an object storage. Object storage is highly scalable, and it's allowed to be shared across lots of different services. You can deploy one object storage, and lots of things can use it. And it's intended to be very, very low cost. The types of things stored in object stores are pictures, images, all of these things, email. And object storage has become very flexible and cost effective because of the types of storage. Gmail, when it first came out, right, everybody was given like a gig of email space, and we were happy for it, and we thought that was enough, and then we all realized how little a gig actually is, and then we got some more, and we got some more. Dropbox comes out, and everybody gets a gig originally, and now I think you can get like gigs of data. The reason that these service providers can provide that access is because of object storage. They have a way to very low cost and scalably provide storage on the cheap. Now there's some challenges with object storage. The way you access the files in the objects is over HTTP, the HTTP protocol. HTTP is great if you're going over the internet to browse Facebook or play a game or download a file. But HTTP as a protocol is really, really slow when it's compared to something like NFS or iSCSI. And so object storage is not a solution for like a data store or something that's transactional. So you can't just replace everything with object storage. It has to kind of fit into this type of a framework. If your application is already relying and working over HTTP, object storage is a great way to offer these capabilities. Now, a future feature of My Hero might be to deploy object storage. What types of things might I put in there? Well, I could have a bucket for pictures. Today, every image, every Docker container for the web server has all of the images for all of the characters into that running container. It's part of the image. For my demonstrations, that's not a big deal. But if this was a production application, and I had thousands of these, and I had to pay for all of the storage space for each one of those running containers, that would be very inefficient, right? So I could take all of those images, put them into an object store, and then when a web server, when a web page would pop up, it would just request the image necessary from the object store. Much more efficient, much more cost-effective way to do it. Similarly, Web applications often have this concept of static files. What static files tend to be inside of a web application are things like cascading style sheets or JavaScript files. Right? They're just pieces other than the actual HTML or logic of your application, components that probably your developers didn't even write. They're just using from some other service that's there. And so again, those don't have to be in every single one of my instances of my app. I could go ahead and put those into an object. This would allow me to optimize that UI service for space, dynamic content, all these pieces. It's not there today. Something I could implement in the future if I wanted to, but this is why object store is used in many actual real production applications. It's for cost, it's for efficiency, for centralization. I don't need to repeat that same file in every single running container. Just put it in one place. Object storage by nature is already scalable and resilient until when S3 goes down and the internet cries, but it's intended to be scalable and resistant. So let's look at another demo at kind of how some of these building blocks and the actual application looks as it goes through. I think I hit the wrong button. That's back to there. Here's mine. All right. So this application, my demonstration application today, is running in a Kubernetes cluster. So it's a microservice app running in Kubernetes, and my Kubernetes cluster happens to be running in Google Cloud. But the fact that it's running in Google Cloud is irrelevant. That just happens to be where it goes through. And so here we can take a look at the Kubernetes dashboard and see the different components of the app. So if I come down here and I look at deployments, and here's where I'll see if I've timed out my time, and I didn't. Go back and get token. Everybody get my secure token there? All right. So back to my namespace. Where is it? There it is. And so here under deployments, inside of Kubernetes, deployments refer to typically a microservice. And so if I scroll down, where are they? So I have a lot of different applications that run. But here we can see the different MyHero apps. And so there's the MyHero data. Still, you can see just one of them running. We can see the application tier, the UI tier, different ones going through. And that's where the application goes in. Now, application developers use the web UI for Kubernetes. They're going to use the actual command line utility for it because nobody wants to use a web UI. And so here I have kubectl. I'm going to make this a bit wider. kubectl is the command line utility for interacting with Kubernetes, right? And it's how you talk to it, how you start new services, how you manage and administer the services that are there. Now kubectl, and then you would add in things like your server, your namespace, and all of those. I've created an alias called just kh so that I don't have to type in the namespace and some of those pieces. It's just kubectl and then the namespace that's there. It saves me some typing. And so let me clear my screen. So kh get deployments. Oops. And so here, same data that we saw on the dashboard. We can see the MyHero app and different pieces that are in there. Make it a bit bigger. Now, if we look at something like MyHero app, here, we can see that I have a desired count of 3, so I want to scale that up. And I have a current count of 3, an up-to-date count of 3, and an available count of 3. The deployment is just the definition of that microservice. Under the hood, each independent container is represented as a pod. So if I do kh get pods, you'll see here is where the actual 3 running, I started in the wrong spot, the 3 running application pods are that represent the service. And underneath that, you'll see the one data service. It's been up for a year, still running stable as it goes through on the pieces, and some of the other chatbots and things that I'm running. With Kubernetes, I get the ability to go ahead and actually check on status of things. So I can do something like kh get logs, and then I could get like the logs from Ernst, who does the counting. And it will, oops, is it just log, maybe? No, here's where I'm going to go to my cheat sheet and figure out what the command was I actually wanted to type. No, it's not get, it's just logs. So kubectl logs, you give it the thing, and then in here you can actually see all of the votes, like Ernst counting the votes as they go in. And so when we deploy to microservices, we still need access to all of that operational data. So as a DevOps engineer, I can see what's going on with each of the pods that are there. Now normally, all of this data for each of these running containers would actually be centralized to a centralized logging system. And Kubernetes and other platforms have the ability to offload those things to things like Elk Stack or bring all this data together. But we can get access to it all very simply as it goes in. Get services. So services in Kubernetes are where some of the load balancing factors come through. So we can see here, so My Hero app. If I go to My Hero app inside of the cluster, I have a single IP address that would load balance across all of the potential pods, the potential containers that are running for the application service. The service here, this is internal to Kubernetes only. For an external perspective, that's where the ingress comes in. So I can say describe ingress My Hero. There it is. And so this is the actual full-on reverse proxy elements that come through. So you can see that this is the actual public IP address assigned to this application. And if you do a DNS lookup on myhero.imapex.io, it'll be that IP address. And so when that request makes it to the Google Ingress controller, it looks at the that it came in for. It says you're looking for myhero.imapex.io, and it then sends it off to the MyHero UI service on port 80. If you make a request for api.myhero.imapex.io, the IP will be the same, but it will send it off to the service for MyHero app. As network engineers, we often think about load balancers in the land of like layer 3 and 4, IP address and ports. In the modern world, when we're talking about load balancers and reverse proxies for applications like this, we're almost always thinking about them at layer 7 layer, where we're actually load balancing. It's all one IP, so many of those as they go in, but the host determine where to send the traffic off to. Is my mic cutting in and out? Is you got? Okay, I'll keep going. You guys can hear me, I'm loud. All right, so we've got the information that as it goes through on there. Now from a scaling perspective, right, normally what you would do is you have a monitoring system watching the status, the incoming traffic that goes through, and then if it saw an uptick, like traffic started to go up, it would automatically scale up a service that goes through. I can also do that manually, so if I do kh scale, and so here's the command where I can go through and scale how many counts I want. So currently there are 3 instances of the MyHero app service. There's 3 running containers. We saw that before. I'm going to scale it up to, we'll say 10. So I'll say scale replicas 10, so give me 10 count of those. I'll hit enter. It's been scaled. Kh get deployment. We'll see if I can erase it. Deployment. MyHero. Yep, I got it. All right. So here we can see now it says desired is 10, current is 10, up to date is 10, but available is 3. The difference there is in the time that I hit it, it was able to start up the 7 additional containers, but they haven't fully processed, their health checks haven't passed. And that available piece is watched before those new instances are put into the service pool for use by the load balancing. I don't have to manually add these additional ones. Once they are available, which should be by now, yep, they are, they immediately get tied back into the underlying service and ingress controller. So no ticket to open to add additional 7 servers for scale as it goes in. Automatically handled. Part of the platform as they go through. Let's see if there was anything else I wanted to talk about. Oh, that was it. All right. All right, so we talked about the different components that are there. Let's talk a bit about the actual client side. We spent a lot of time on the microservices. Let's talk about how the clients are looked at from an application developer's perspective. The user interface is how we actually interface with an application, or how a user would interface with an application, right? Fairly self-explanatory. But if we dissect that, what does it really mean? Applications today are so much more than just a web page. Let's think of an example like Twitter. How many people are on Twitter? Anybody else? I'm on there? Okay. If you use Twitter, how many people use the web page for Twitter? Yeah, a few. How many people also use maybe a mobile application? I remember when I first got my Apple Watch, I thought it was great. I could get all my notifications on my Apple Watch, and then I thought it was terrible because I got all my notifications on my Apple Watch. But you can. I've turned all mine off, but you can. So you can get it accessed on our wearable technology. And then we also have the ability for the Twitter application to be consumed by other applications. Things like if this, then that, which is an event-based kind of action system. And so the big thing now for a lot of folks is every time I write a blog post, I want to make sure I tweet about it so people know that it's there and they go read my blog post. But it's really boring to tweet every time I write a blog post. And so we can actually tie using services like if this, then that, into WordPress and Twitter. So every time I update a new blog in WordPress, send a tweet out. Or my personal favorite, every time somebody follows me on Twitter, say thank you. There's nothing like a heartfelt automated thank you to make me feel warm at heart as it goes through. So applications are more than just this intended initial web application that goes through the web front end. And so I tackled this for my hero, right? At this point, I was still good. My application was running. What am I going to do next? And I said, all right, well, I want my hero anywhere. I had the web page. I wanted bots, right? I wanted SMS messaging. Not everybody has a smartphone. Not everybody might be on WebEx Teams. But most people have a phone where they can send text messages, SMS messages. So can I vote through there? And then, how many people have an Amazon Alexa or Echo device or Google Home or any of these devices? They're starting to pop up all over the place, right? I thought, wouldn't it be awesome if I could talk my votes in? These are the types of things that are out there. And application teams building consumer-facing apps have these same ideas. I want to get my application in as many places in front of as many users as possible. What's nice about the way the architecture is we talked about the My Hero application. I've got an API layer. The web UI is written using those APIs. The Teams bot, then it was known as the Spark bot, was the first one I wrote. I used the same APIs, and so it was pretty easy to write that. I already knew the APIs to make a vote. I knew the APIs to get the options, get the results. I just had to wrap it up in a chat interface. And so I learned a little bit about the Spark APIs, now known as Teams APIs, and I built a chat bot. So that was pretty easy. And then I said, well, Tropo was a Cisco service that we could use for text messaging. Basically, almost the exact same code I did for the Teams bot, the chat bot, and just replaced sending it through Teams to sending it to Tropo. And so moving from Teams to here was, I think, an afternoon's exercise to make the change. And then as I was heading out to do another demonstration, I was on vacation the week before, and I was in the Black Hills, where in the US, it's where the Mount Rushmore is. There's all sorts of cool stuff. It was late one evening. My family had all gone to bed. I was sitting on the front porch of the cabin. Fire was going. I wasn't tired yet. I said, wouldn't it be cool if I could do this Alexa thing? And so in about 2 hours on vacation, sitting there with a fire going, I learned how to write Alexa skills and take the code that I had already done and port it over. And that's what's nice about these microservice applications in the architecture. Because they're all API-driven interaction, the building blocks are pretty easy. We can jump from one interface to another. So supporting all of the different types of interfaces isn't a huge challenge for most application teams. It's just a matter of kind of adjusting as necessary. As long as the application itself was built with kind of those APIs and that interaction layer there, we can consume it just about anywhere we want. And so for the Alexa one, this is where I decided, let's bring in the new big guy, right? Serverless. And so if you've seen me speak before, maybe you're familiar with Captain Cloud, API Girl, and Carl. But everybody, when we hear this idea of serverless, we think, oh, this, right? We just throw our servers away. We don't need them anymore. Serverless computing is not that, right? We still need servers. Something needs to run the code. What serverless computing is about, it's a perspective. It's what do we talk about? What is the developer? It's all from the developer's perspective. What does the developer care about? And serverless computing is simply an extension of what we already had from virtual machines and then containers and then serverless. Way back in the day, before the x86 virtualization initiative, right, application developers needed physical servers, right? I had a coworker that used to work in Microsoft way back in the day, and all of their developers, under their cube desks, had like 5 different physical servers running different versions of Windows and Server and all the things that they would do. And then x86 virtualization came around, and developers said, thankfully, I don't have to worry about hardware anymore. I can just deal with VMs. And so they had one server. It was bigger, but it ran everything on there. So I don't have to care about the physical anymore. I just care about virtual machines. That stayed around for a long time. And then we got to containers. And the developer said, you know, I don't even want to worry about like virtual machines anymore. I just want to worry about my code and what my dependencies are. So Docker containers, container technologies, my code, whatever my dependencies are, I'll package it up and we'll just run a container someplace Another layer of abstraction, taking the developers farther away from the underlying servers that are there. It's the journey we've been on. Serverless computing is the next step in that. Developers have gotten to the point, they're a bit high and mighty, they're proud of themselves. They say, I don't even want to worry about containers anymore. I just want to give you my code and let somebody run my code when something happens. And so the way that serverless functions is it's this event-driven idea. It allows the developers to focus on their code, and so something happens in the world. Maybe somebody sends you a bot message, an alert happens, an IoT trigger, just some event happens. That event then kicks off an execution of whatever code the developer wrote, and that code will reach out to the data services and the objects and then respond to it. Right, from a developer's perspective, this is what serverless is. I write code, I set up some sort of a trigger, so an event happens, my code runs, everything's fine. It provides built-in scaling, it's very efficient, and frankly, you can do a lot of serverless very cheaply in different types of cloud services that are there. The secret under the hood is that serverless, not only is it not without servers, because that code has to run someplace, is nearly all serverless platforms, all the ones I've run into, but maybe in the future we'll have different ones, but the ones that I've looked at, under the hood, really all it is automatic containerization. It's taking the necessity to write a Docker file away from the developers and saying, we'll take care of that for you. The serverless platform will take care of that for you. And so the developer provides the code and says, this code is Python or Ruby or Go, right? They say, I've written you this code, here it is. And then the platform on which the serverless is running takes that code, puts it into a Docker container, and then runs the Docker container every time an event happens. So serverless is not only not serverless, it's also not containerless. It's just making it so the developers don't have to pay attention to it. Right? Somebody has to. Somebody build the servers, maintain the infrastructure, provide the serverless environment. But that's what serverless really is today. It's event-driven code, automatic containerization. So for the MyHero Alexa interface, right, the suggestion from Amazon to write this is to use their serverless technology, which is Lambda. Right? It's up in the cloud. It's one of their services. Great service, works fantastic. And so what I did is I just took the same Python code that provided the chat interface, and I just wrapped it in the voice structure from Alexa and run it in AWS Lambda. Just took a couple of hours to learn it all to provide that interface as it went in. And so the architecture of MyHero today looks like this. The base of this is all basically what we've seen. But what I've added up at the top were additional client opportunities. In addition to the upgraded web interface to MyHero UI, we had MyHero Spark. If I was building it today, I would call it MyHero Teams, but it's still called MyHero Spark. The MyHero Tropo service provided the text messaging service that went through. And then MyHero Alexa allows us to do the voice interaction as it goes in. So let's hit our final demonstration and see kind of how these components work as they go together. And so if you want to follow along, I thought it was there. Remember, in the Teams room, it's there, but that's the URL. But let's actually see how this looks. So back over here, we will go to myhero.imapex.io. And so here is the application, the web service that's out there. So as mentioned, I can go ahead and vote for whomever I'm interested in. We'll say Superman today. And so if we were to sit here long enough and votes came in, this is a dynamic page. It'll render itself, move the votes around as they go through. Kind of a typical web interface as it's there. I can also do my chat votes. This will be a little harder to see because I can't make it much bigger. But if I come in here, I can say options. So give it a /options. I think I actually need the S though. Yep. Options. And it will print out the options that are there. Apologize for the folks in the back. But I can do a /vote for Gamora. And it'll place the vote. So I can interact in that way. But the interesting piece is let's see if we can actually get that live demo of the voice interaction to function. This is the audio one. Yep. Excellent. Let me see if I timed out my login. I did. So I'm logging into Amazon's developer environment, and then for the Alexa skills, and we can see I'm on the MyHero demo skill. And so inside of the developer console is where you could actually go through and see the components that it takes to build the service. And so here on code is where we would see the, this was built before some of the newer features for Alexa go through, but it's Python code that's running under the hood. But they've added this test capability. I keep popping my letters. they added the test capability. So I can actually go in here and interact with this over voice. And so let's see if it works. Open My Hero.
Welcome to My Hero. Let's figure out the best on-screen superhero. Would you like to hear the options?
Yes.
The possible heroes you can vote for are as follows.
So as she's reading
Captain
all the
Cloud,
options, what's
Spider-Man,
nice as a developer
Captain
as I look
America,
at this,
Batman,
is it shows
Superman,
me all of the API
Wonder Woman,
interaction all
Deadpool,
over the place,
Black
and I
Widow,
can kind of see
Iron
how
Man,
things go.
Star-Lord,
To
Scarlet Witch,
retrieve this
Gamora.
list, it made a
Who would you like
request
to vote
out to
for?
the system to retrieve the options, and then Alexa just reads them out. And then I can say, Captain Cloud.
Thank you for your vote for Captain Cloud. It has been recorded.
So it's those same APIs that were used for the Teams bot and the web interface. Very simple to add these additional interfaces. But exposing all of these capabilities back out there, this is what it takes to be a modern application developer building real applications today. Is you have to follow the hype. You have to follow the users and make sure that you're there wherever the users are. And these are some of the pressures that our application developers have as they tackle these. So we've talked a lot about the code that's in there. Let's talk about the process of actually turning code into an application. And so the development process starts with the development, the coding, building all of the scripts, the Java code, the Python code, whatever it is. And then it gets into a pipeline that turns code into applications. The first step in that pipeline is the integration phase. Most applications have more than one developer working on it. And so the integration phase, we take all of the code from all of our developers and we combine it together. We integrate it together into whatever our application really will be. And then we execute tests to make sure that that application is doing what it's supposed to do. Integration phase. Usually integration and testing go in. This is done by integration and test engineers to assemble all of these pieces as they go through. Now, assuming the tests pass, we then move along the pipeline into the delivery phase, software delivery. Ideally, only tested and working code enters the delivery phase, but we'll leave that for another discussion. But we take our working code and we package it. We package it up in a way so that users could potentially use it. And so this would be creating what we often call artifacts inside of the development world. An artifact will depend on the type of application you're working on. So at Cisco, if this is the development team for iOS, their artifact is going to be a final bin file that we might post to CCO. If you're building an application like Call Manager, the artifact might be an OVA that you would download and deploy as an OVA. If you're a mobile application developer, the artifacts are those mobile apps, right? Those pieces that go in. Or maybe it's a container image. These are the artifacts that are your application. They get created in the delivery phase by packaging engineers. And then finally, we get to the software deployment phase. In the deployment phase, this is where the ops guys come in. They take all of those artifacts, they take the information, they take what's necessary, and they actually deploy it. They configure it for use. They put it in the hands of the users so that the code can actually do something of use that's out there. So software integration, software delivery, software deployment. That is the delivery pipeline. That's how it's been for years. And again, each step along the way traditionally has been people. Integration engineers, packaging engineers, delivery or operations engineers. Continuous development is an evolution of that pipeline process. As the world of the software development engineers sped up and business leaders and customers demanded things to happen faster and faster, that pipeline became slow because of all of the manual steps and handoffs that were in there. And so continuous deployment and continuous development is all this idea of, can I automate that? How can I make that work faster? Each step needs to happen, but we want to see, can we make it work faster? And so continuous development is the same basic process flow. But instead of software integration, we have continuous integration, CI, where we have automation tools that actually do the same types of things that were necessary for integration and testing. And then continuous delivery. Right? Once we've passed tests, we then automatically create those OVAs or images, and we put them into the appropriate artifact repositories that will hold them until they're needed. And then finally, some organizations go all the way to continuous deployment, where once known working code has been packaged and made available, we automatically deploy it. Now, different organizations will have different levels of continuous development that meet their needs. Some organizations are happy with just continuous integration, right? Let's just get it integrated and tested every time a developer writes a code, and we're good. Many organizations say, you know what, I'll do continuous integration and continuous delivery. I want to make sure once my code has been tested and passed, I want to package it up and put it in the artifact repositories. That's good enough. And then there's the really advanced folks that are out there that say, no, if I've got code that's been tested and packaged and we feel confident that it works, I want it in front of my users as fast and as soon as possible. And so they go to continuous deployment. And so we often say CI/CD. I sometimes say it's CI/CD/CD. There's 3 phases. Organizations will figure out what means to them as they go through. Now to apply this to the My Hero application, the way that this process would look is there's me as code lord, my happy little application developer, and I work on my development environment, just like we saw in the demonstration. When I have made my updates, I will go ahead and commit my code and push it up to GitHub, source control. GitHub is then integrated. I've registered what's called a webhook with GitHub that says every time my code is updated, please go notify my CI/CD server. For this example, we're using drone.io, which is an open source CI/CD server. So GitHub notifies Drone there has been a change to the code. Drone then kicks off the build pipeline process. It'll do the integration and test. It'll pull the latest code down, it'll integrate it, it'll run the application, test it, make sure it's good. If everything is good, it'll build the container images on the Drone system. Those container images need to go someplace so that they can be used. So Drone will then push them up to an artifact repository. For this example, it would be Docker Hub. So we take the Docker images, we put them in Docker Hub so everybody can use them. Now, if I want to go all the way to continuous deployment, Drone may then communicate back out to Kubernetes and say, hey, there's been an update to the application, deploy a new instance of the application. In order to do that, Kubernetes would pull the new images from Docker Hub so that it has the latest code to run. And at the end of the pipeline, Drone sends a status message out to WebEx Teams that I can read. So the entire process from GitHub to Drone to Docker Hub to Kubernetes, all that runs in the background automatically. And if everything is successful, all I'll eventually see is a status message that says everything is good. If something went wrong along the way, I'll get a status message that says there was a problem, and I can start to go into the logs for the system and see where the potential problem might have been, and then ideally resolve that, and then push changes, and the process will continue as it goes in. Continuous development. That's what the application developer wants to live in that type of a world. Now let's take a moment to go back to the infrastructure necessary to run these types of applications, which is one of the points we wanted to hit. So if this is what people are building, our application guys are doing this, how do we have to support it? What does it take to successfully build an application like this? You guys probably all know, right? It's a cloud. I need a cloud. This is where cloud kind of came from, and this is why application developers so often went to public clouds, because they provided a platform and services that they could interact with in this way. And so as infrastructure engineers, we've often tackled that and said, okay, that's great, but we build infrastructure for our organization, not Amazon. And so we're going to build ourselves a cloud strategy, and we are going to go after this, and we are going to build the unicorn of clouds. How many people have been on a unicorn project? Right? We've all been there. I've done several where we set out, we understand our requirements, and we go after it. We're going to build a powerful unicorn of clouds to solve all of my application developer problems, because I understand what my application developers need. I may not have asked them, but I know what they need. And at the end of our project, we don't end up with a unicorn. We end up with a sad little donkey corn. Kind of looks like a unicorn, but not quite the same, and nobody's quite as satisfied. And the reason is we can't take what we've just done in the past and layer a little bit of automation and maybe some self-service portal on the top and say, here's what we've always given you, but now you can click a button and get it instead. Aren't you so happy? Right? And application developers often say, no, we're not. And I've been in lots of those conversations. And so let's wonder why. Why have we seen so many donkey corns when we wanted to deliver a unicorn? And it's fairly obvious if you think about it after our conversation. It's because something I like to call the cloud gap. And the cloud gap is right there. It's where our users and developers are at the top, and they just want to develop. They want to work in their development environment, and they want to use the tools that they have. And then down at the base, the infrastructure engineers, guys like us, right, we deliver infrastructure and operating systems. And for years, we've said, here's some infrastructure and some operating systems. Go put your applications on it. And the cloud gap was always there, but it was bridged through brute force and binders of runbooks and gut feeling and troubleshooting to take the infrastructure and operating systems and make the code work. Right? That's just how we've bridged it. But with the demands and the speed that's after, like we can't do it the old way anymore. And so to bridge the cloud gap, we have these initiatives, right? And everybody in every organization, whether you're an architect, an infrastructure guy, or an application developer, we all want to solve this problem. And so we tackle it from both sides. At the base, our architects, our operators say, okay, fine. We'll add some cloud management, some automation, right? We'll give you some capability for some self-service, and there's plenty of tools that have been delivered in the open source and from vendors to try to achieve that. And application developers have come down and said, okay, well, we'll start to do some automation in the delivery pipeline. And this is where things like Bitbucket and Jenkins and Puppet and Ansible and all these tools to try to automate actually taking the code that they wrote and making it ready for use. But we're still not done. And this picture here is a donkey corn. I've seen so many organizations that thought, hey, we've given you some self-service. You can get your infrastructure as fast as you want. Click a button. How many VMs do you want? And developers are like, I don't want VMs. Like, that's not enough. There's everything else necessary. All the pieces we've talked about over the last hour and a half. There's the applications and middleware, queuing systems, caching services, new database systems, containerization, scheduling, placement. All of these things have to be tackled as well. And in order to bridge the cloud gap, to deliver an actual unicorn of a cloud, somebody has to provide that. Right? So the question comes up in organizations. Do the developers and the users start to come farther away from code and deliver it? Do architects and engineers and infrastructure folks move up and try to just do more? And I've seen both of those try, and they tend to not work terribly well. The successful nature happens when organizations come through and say, okay, we're going to insert a new layer of folks into this, right? Our DevOps engineers. And the DevOps engineers say, we'll bridge the cloud gap in its entirety. We'll take over cloud management and automation all the way up to delivery pipeline. Infrastructure architects and operators are still needed. Like, somebody still needs to do that. And the software developers want to just do their development. The question often comes is, where do DevOps engineers come from? Do they sprout from the fertile ground of burned out donkey corn clouds, sprinkled with unicorn tears and fairy dust? That would be awesome, right? It's a movie in its making, right? But that's not where DevOps engineers come from. DevOps engineers come from the two ends of the spectrum. There are a lot of really solid systems engineers and infrastructure engineers here at Cisco and at other customers I've talked to that for years were hardcore router guys or switch guys or server guys. And they got interested in a bit of coding and some DevOps pieces and have moved up the stack, so to speak, into a DevOps engineering role. And there are plenty of software development folks that have come out of college and comp sci and said, you know what, I do not want to write Java for the rest of my life. But you know what, all of this open source tooling around big data and automation and Jenkins pipelines, that's pretty interesting. So they drift down. DevOps engineering teams are made up of people from both sides of it, right? They assemble and they bridge that gap really effectively because they have, as a joint skill set, knowledge of both ends of it. Now, I've talked about this in a cloud, so let's throw some cloud terms up there. If you're thinking in the layer of the bottom three layers, that's infrastructure as a service, right? Cloud management, automation, operating systems, infrastructure, that's infrastructure as a service. On top of that, everything else is platform as a service. And there are options to either build your own infrastructure as a service or platform as a service, or buy one as a commercial offering, or maybe use an open source solution that's there. What's interesting to me is that organizations can mix and match those. Maybe you're a big organization, you've made a major investment in your data centers, you have a lot of infrastructure, you've done a good job at operationalizing it, and so you say, we're going to build our own custom IaaS platform. But our application developers have some fairly specific needs that are met by a commercial platform as a service offering, and so on top of your custom IaaS, you just put OpenShift from Red Hat. Or maybe it's the other way. You say, you know what, we have very custom platform as a service requirements, pipeline needs, very custom specific nature there, but we could care less what our infrastructure is. And so you leverage something like AWS or Google for the IaaS, but you build your own do-it-yourself on top of it. So organizations can mix and match all these pieces as they go through. When you look at the slides, I've added a few examples of where different tools fit in, but it's just a few examples. If you want like the holistic list, I always recommend folks go check out the Cloud Native Computing Foundation, and they have what they put together as the landscape. And they used to do it as a poster like this, where you could get all of the logos categorized, and then they finally gave up trying to like get them all onto one page. And so now it's a dynamic web page as it goes in. What I like about the landscape is that every week it feels like there's some new funny misspelled word that's an open source project, and I have no idea what it does. But if I go to the CNCF and I look up that project, it puts it in a category. And I'm like, oh, that's a config management tool like Ansible. I know what it does. Or that's a big data database. I kind of know what it does. So I can start to categorize them. It's a great resource to take a look at as you go through. Now we are, believe it or not, coming to the end of this. So in summary, let's kind of close down. Now, 2 hours ago when we started, I said there were 3 learning objectives that was my goal coming out of this that you would be comfortable doing. So let's see how I did. After 2 hours, does everybody feel like you could describe what a microservice architecture is and how it differs and why it fits in compared to a client-server app? How did I do? Anybody? All right, excellent. Those common building blocks, caches, queues, object stores, why application developers are using them, the problems they solve. Do we feel pretty good about those? Excellent. And then finally, our last section was all about the traditional architecture of x86 virtualization and what we have to do to optimize that and make it fit these modern requirements. We feel better about that? Excellent. Remember that when you fill out your surveys. So one of the last things I want to point out is one of the most exciting announcements this week at Cisco Live from my perspective is the changes and the adoption of these new skills and these new topics that have been embraced throughout Cisco all the way to the Cisco certifications and learning. And so if you're interested in these topics and how automation and programmability and how cloud and DevOps fit in, the new DevNet certifications of DevNet Associate and Professional and future DevNet Expert offer you an opportunity to adjust your own learning and your own skill sets to factor into those areas. And along the way, if you're still more focused kind of in the network infrastructure space, we've also taken all of the knowledge necessary that kind of goes into somebody focused on programmability and offer those as options that you can pull in. And so if you are a CCNP candidate, you can take the core test around network professional pieces and say, you know what, I'm interested in DevOps, or I'm interested in automating my data center. And so you can take the automating and programming Cisco data center infrastructure, whatever the full real name of the test is. And that will achieve your CCNP with a specialization in a programmability topic. And then you can use those as you go through. Check out developer.cisco.com/certification for full details. It's also on Cisco Learning, but it's a really enhanced element, and it shows the commitment that Cisco understands that this is where all of our engineers, where internal and external and with our partners, need to have skills from both traditional infrastructure as well as the programmability side as it goes in. If you've got any more questions, please feel free to stay in touch. I'm hapresto@cisco.com or hfpreston on Twitter. I will be following that WebEx Teams room for this event, so if you're on Teams and you want to send messages, that's a great place to go. Happy to communicate there. And then be sure to follow Cisco DevNet on all the social medias as they go in. I have about 5 minutes left if there's any questions in the room that you want to ask live. One? Excellent.
Are you part of that expert design team?
For the certification? Yeah. So the question was, am I going to be part of the expert certification design team? The work on the DevNet Expert hasn't started yet. A lot of the focus has been on the associate and professional level to get those off. I imagine as we start to dive deeper into expert, there'll be areas where I'll have a chance to contribute, give some suggestions as they go in on that. Okay. Any other questions? No? All right. Well, as I close down to the requisite slides that they make me put in, just a reminder that you can find that WebEx Teams room in the Cisco Events app. And do please complete your session evaluation. I really do mean it. Every one of the speakers here at Cisco Live, check these out, not just because we want to make sure that we get the awards, but because we want to know that we've given you what you were after, right? We want to understand, did we meet the demands that you had? We want to see, what do you want next year? What extra pieces we can help as you're adjusting and learning new pieces on yours. So I look forward to seeing all the feedback from everybody, as are all the rest of the presenters for the sessions that you've checked out. And be sure to continue your education through the Cisco campus in the World of Solutions. Sign up for a Meet the Engineer, or new this year, a Meet the Developer in Cisco DevNet. You can sit down with one of our developer advocates and experts. Check out the self-paced labs or all of the related sessions in the cloud track. We're very early in the week still, so there's plenty of excellent content still out there. With that, thank you so much for joining me this afternoon after lunch. You've been a wonderful audience, and I'll see you soon. Thanks.